So we're going to spend 2 days covering op amps, and I'm trying to decide how much I want to cover today and how much I want to cover on Friday. Because to be entirely honest, we could probably cover practically everything today, but it might be a good idea to get you guys some practice, okay? So an operational amplifier is an integrated circuit, all right? So it is not, I mean, it absolutely is a circuit component, meaning that, well, if Radio Shack still existed, you could go over there and buy one, but now you'd have to buy it from Mauser, DigiKey, Amazon, and all that kind of good stuff. So it is a component, but it's a chip, okay? So it is not a two-terminal device. This is the first thing that we're going to be dealing with in this class that is not a two-terminal device. So a physical op amp chip looks something like this, or at least the ones that we are going to be dealing with. We have a box, and there's either going to be a divot cut out in the top, or there's going to be a dot in the top left corner, and this lets us know which pin we have. So pin 1 of our op amp, whatever type of op amp it is always the one to the left of the divot or the left of that little circle. And then typically speaking, there will be 2, 3, 4, 5, 6, 7, and 8 terminals. Okay. For the most part, we don't have to deal with all 8, but I'm going to talk about what they are. Okay. So let's start by saying this is what a physical op amp actually looks like. It is not how we're going to see it in a circuit. Okay. The schematic representation of an op amp is going to be something like this. It's a triangle. And our important pins are these 3. Okay. This pin right here is what's called the non-inverting input terminal. It's denoted in the schematic diagram by the plus sign. This pin right here is for the inverting input terminal. And it is denoted by the minus sign. You need to absolutely pay attention to where the plus sign is and where the minus sign is, because we can flip this guy over and have the minus sign on top. That's always the minus sign is always the inverting input terminal. Okay. So it doesn't matter if we have it plus sign on top or plus sign on bottom. The plus sign is non-inverting input. The minus sign is inverting input. Their physical location means nothing. All has to do with the plus sign and the minus sign. Over here on the opposite side of the chip, we have our output terminal. Okay. That's 3 of the 8. Now I'd like to briefly talk about some of the other pins that we aren't really going to utilize in this class too much, okay? The first will be a pair of terminals. I'm going to draw them here and here. And I'm going to call this guy VCC plus, and this guy down here VCC minus. For the actual operation of an operational amplifier, these 2 are critically important because this is how we power the amplifier. So an op amp takes a positive DC voltage and a negative DC voltage to work correctly. If we do not power the operational amplifier, it does not do its job of amplifying our signals. All right. So this is another new thing. This is the first component that we're dealing with that doesn't just do what it's supposed to do. We absolutely must power this in order for it to work, okay? Then there are two other pins called offset null 1 and offset null 2. We will not ever use these pins in this class, okay? These pins exist because microfabrication is prone to errors. So what could happen, and actually regularly does happen, is that you could apply a voltage to the VCC plus pin. You could apply a negative voltage to the VCC minus pin so that your op amp is on. And then you could ground the non-inverting input terminal and ground the inverting input terminal, but still see a signal at the output. So those offset null pins are there to correct that, to be able to bring that voltage when you have no voltage at the input, bring the output voltage back down to 0. And again, that voltage at the output arises due to manufacturing errors, okay? Nothing that we can control about it. Not all op amps actually contain those pins, but the classic 8-pin dip chip absolutely usually does. So I just wanted to mention it.
Offset null over fan as well.
So that's just allowing you access to be able to apply a voltage or some elements to be able to move that offset voltage around. So it can't fail because it isn't a thing. No, VCC is for applying positive power. VCC plus is for applying a positive voltage to power the chip. VCC minus is for applying a negative voltage to power the chip. If either of those pins fail, the device just doesn't work, period, because you can't power it. All right, so the terminals in black are the ones that we are going to be dealing with regard to our circuit analysis, okay? So the circuits that we are going to be dealing with are going to be a very specific type. In this class, we are going to be dealing with, let me change this to black. Negative feedback ideal op amp circuits. Literally every circuit that we deal with here in circuits 1 will be of this type, okay? When those of you who go on to take circuits 2, we will break every one of these rules. It will no longer be negative feedback. It will no longer be an ideal op amp. We'll talk our way all the way through stuff. But for general circuits purposes, we're going to leave things negative feedback and ideal op amps, okay? So let's talk about what a negative feedback circuit is, particularly as it pertains to an op amp circuit. So let's say that I have an op amp. I have my my non-inverting input terminal here, my inverting input terminal here, my output terminal over here on the right. All negative feedback means is that there is a component which is placed between the inverting input terminal and the output terminal. That's negative feedback. Right. Absolutely. So in all of the circuits that we are going to analyze in this class, there will be something. Could be a wire, could be a resistor. We now know enough. Technically, it could be a capacitor or inductor as well. Might be a voltage source. But something that provides a connection between the inverting input pin and the output pin. That's what negative feedback means for the purposes of this class. Okay. So now let's talk about an ideal op amp. So I'm going to open up a file here. Might take me a moment to find it, so bear with me. This is a data sheet for a Texas Instruments 741 op amp. There is a crap ton of information. Here's the simplified schematic: input, output, inverting input, non-inverting input, output, offset pins, all that kind of stuff. They don't even put the power pins on their thing. Whole bunch of text and all kinds of stuff. Our pin configuration, like I said, a little circle on the top left, and then 8 pins. Blah, blah, blah. All the specifications, couple of circuits and all this kind of stuff. Doesn't have anything to do with you. Here we go. Let's make this smaller. How do I make this smaller? Exactly. Yeah. Oops. If I saw this on an exam, I would cry. Okay. So this is a simplified look at the internal workings of an op amp. For those of you who want to continue dealing with me for 2 to 3 more years, I teach a class on op amp design where we break it down into building blocks and all that kind of stuff and wire stuff together, okay? This ain't that class, not even close, all right? We are going to represent this horrifying conglomeration of 22 transistors, which you guys have no idea how they work. Well, maybe a little bit because you talked about them in Engineering 120 series. Very briefly, you just use them as a switch. They don't work like switches here, for sure. 11 resistors. I hope you guys all know how those guys work. 1 diode, and then 1 capacitor, okay? This looks extraordinarily complicated. And internally, it is extraordinarily complicated. But the ideal op amp obeys 2 very simple rules, okay? Number 1, no current can flow into or out of the input terminals. Okay. I'm going to be very clear here. I'm specifying that no current can flow into or out of the input terminals only. All right. So current can flow into or out of the output terminal. Current can flow into or out of our power supply terminals. Current can flow into or out of our offset null terminals that, again, we'll never use in this class, okay? Rule number 2. Says that there is no potential difference between the input terminals. So this means that the voltage present at the non-inverting input terminal, which I'm going to label as V superscript plus, must be the exact same voltage as the voltage present at the inverting input terminal, which I'm labeling V superscript minus. Okay. These two phenomenon occur for vastly different reasons, but they are related. Okay. In a practical op-amp circuit, almost no current can flow into or out of the output, or excuse me, the input terminals, because the op-amp has a very, very large, what we call an input resistance. Okay. All the resistors that we've been dealing with in this class are on the order of hundreds of ohms to kilo ohms and all that kind of stuff. For a BJT, or a bipolar junction transistor based op-amp design, that input resistance is on the order of a few mega ohms, so millions of ohms. For a MOSFET based op-amp design, it's usually on the order of 10 to the 12 ohms. So not mega ohms, not tera ohms, 1,000 times larger than that. Okay, or no, actually it would be tera ohms. Not mega ohms, not giga ohms, tera ohms. Yeah. So if all the resistors that we are dealing with are on the order of kilo ohm scale, and they get connected to something that has a resistance on the order of mega ohm or higher scale, practically no current will ever branch off and flow into this guy. So that's why rule number 1 is true. Okay. Rule number 2, there is no potential difference between the input terminals, has to do with what's called the open loop gain of the system. This is going to mean next to nothing to you guys, and that's perfectly okay. But an operational amplifier's open loop gain, when we don't have any resistors or anything like that in a feedback position, is pretty close to a couple of 100,000. Meaning, if you're ignoring a lot of things that I'm not mentioning, if you put in a 1 volt signal at one of the inputs, you should expect to get 100,000 volts or so at the output. It doesn't actually work that way, but that's what the open loop gain means. Okay. So that extraordinarily high gain winds up forcing the difference between the input signals, B plus and B minus, to be next to nothing. Okay. So that's where rule number 2 comes from. So just using these 2 rules and our knowledge of circuits, we're going to analyze some things. Yes.
So how does they're vastly different reasons that they're related?
So that internal input resistance, if you analyze this guy using what's called a practical op-amp model, the internal input resistance winds up behaving as both an open circuit and a short circuit at the same time, forcing that voltage drop to be 0, but the current flowing through it to also be 0. It's not remotely important for the purposes of this class that you understand what I just said. These 2 rules and basic circuit theory is literally all we need to know for the overwhelming majority of op-amp problems. Most op-amps are used in a negative feedback configuration, right? Most practical op-amps. So let's talk about some uses for op-amps real quick, since I haven't mentioned it yet. Op-amps are used for what's called analog signal processing, okay? The name operational amplifier came about post-World War II, where these amplifier circuits were made, which performed mathematical operations on signals. So using an op-amp or a combination of op-amps, we can add signals together. We can take the difference of signals. We can amplify signals. We can make them larger. We can attenuate signals, which means we can make them smaller. We can take the derivative of signals and we can integrate signals. So op-amps are used to perform mathematical operations on voltage waveforms. We are going to talk about a little bit more of that later on, but let's just kind of figure out what the heck these things are doing and the rules through the analysis first, and then we'll concern ourselves with that, okay? So the first circuit that I want to look at is this guy right here. So let's say that this current source is 2 milliamps and this resistor is 3 kiloohms. And we want to determine what our output voltage, V out, is going to be. Okay. If we apply op-amp rule number 1, that means that this current right here, I'm going to call it I minus because it's the current flowing into the inverting input terminal, has to be what? 0. So what that means is that all of this 2 milliamps of current has to wind up flowing through this feedback resistor, which will in turn generate a voltage having this polarity. So what should that voltage be? 6 volts, right? 2 milliamps times 3 kiloohms. And now we want to figure out what that output voltage is. Okay. Now this is a little bit harder, but not a whole heck of a lot. I'm going to draw a loop here. Actually, let me make sure we're speaking the same language. So this output voltage, V out, is a nodal voltage, meaning that it's measured with respect to ground. So this voltage right here, V out, represents the exact same thing as the voltage that appears at the output terminal of the op-amp. Okay. So what I can do is I can write a Kirchhoff's voltage law loop starting at this ground, go across my op-amp terminals because I know that there is no potential difference between them. Go across my resistor and then end at ground again. And that is a perfectly acceptable KVL path for me to take.
What did you say? V out plus minus.
V out, as I've drawn it to the right of that terminal, is a nodal voltage, meaning that that voltage is measured with respect to ground. Since I'm about to do a Kirchhoff's voltage law loop, I wanted to represent that voltage as a voltage drop between that node in the circuit, the output node, and ground specifically to better illustrate the KVL equation I'm about to do. Okay? So applying KVL around the green path. So if I start at that ground right here, I see a short circuit, right? So I have no voltage drop. If the voltage present at the non-inverting input terminal is 0 volts, what does the voltage at the inverting input terminal have to be? 0 volts. So the first actual voltage drop I see is the positive polarity terminal of the 6 volts. So I'll have 6 volts plus V out is equal to 0. And therefore, V out must be negative 6 volts. Yes, Ian.
So since you have no voltage relative to input, they also both eventually affect current. That means there's no voltage drop across that current source. That means it's not supplying any power to the circuit effectively.
Yes. If there were no resistor there, that is correct. The output voltage would be exactly 0, even though the fact that there's current is flowing. Yes, you're absolutely right. Okay. So a question that could be asked is, our current source here, we have just determined that the voltage drop across the current source must be 0 volts. Does everybody understand why that is? One terminal of the current source is at ground. The other terminal is connected to the inverting input terminal, which has a voltage of 0 volts, because the non-inverting input terminal had a voltage of 0 volts. So there's 0 volts on both sides of the current source, which means our current source isn't supplying power. Now, our 3 kilo ohm resistor is absolutely absorbing power because there's a 6 volt drop across it, right? So it should be seeing 36 volts squared divided by 3 kilo ohms worth of power. Where does that power come from? The power supply of the op amp. Okay, the op amp isn't magic, but we are not visualizing the power supply terminals here because they don't inform our circuit analysis at all. Okay, but this system as a whole will absolutely still obey all of our power relationships and all that kind of stuff, meaning that the total power absorbed has to equal the total power supplied. Right?
So the current source most of the tapping is away from the voltage.
Exactly right.
Like the current voltage.
Yeah. Exactly what it's behaving as. This is what would typically be called a transconductance amplifier because it converts a current at the input to a voltage at the output. But that is exactly the description of a current controlled voltage source as well. Absolutely right. Another question from somebody? I thought somebody raised their hand. All right. So nobody is saying anything. Let's work another problem. I'm going to make a slight modification to this guy. I'm going to have to do it on the next page. So let's say that we have this circuit. I want to again determine what our output voltage is. Any thoughts on how we should approach this guy? Yeah. Okay, so the voltage here must be 2 volts with respect to ground. Absolutely correct, right? If the voltage present at the the non-inverting input terminal is 2 volts, the voltage present at the inverting input terminal must be 2 volts. All right. So this is actually informing how we are analyzing these circuits, right? One of the first things that we can do is figure out what the voltage present at the non-inverting input terminal is. It's usually very, very helpful because it tells us how the rest of the circuit tends to behave. All right, so by applying op amp rule number 2, we know what that voltage is. If we applied op amp rule number 1 again, we would see that this current is again 0 amps, which means all of this current that's being supplied by our source winds up flowing through the 2 kilo ohm or 4 kilo ohm resistor. Caitlin, what's up? Op amp rule number 1 says that no current can flow into or out of the input terminals. So because of op amp rule number 1. Exactly right. All of the current that is being supplied by our 3 milliamp current source has to flow up through that 4 kilo ohm resistor because none of it can flow into the input terminals. So what's the voltage drop across our 4 kilo ohm resistor? Pardon? 12 volts. So what should be out be? Okay, so I'm hearing some people say 14, I'm hearing other people say -10. Let's do KVL and figure it out, right? Until we get used to this, let's go back to those simple and straightforward rules, okay? So I'm gonna start here. I'm gonna go up, come back down to ground. So applying Kirchhoff's voltage law, I have -2 volts. There's no voltage drop between the input terminal, so I'm just going to jump from the inverting input terminal, excuse me, from the non-inverting input terminal to the inverting input terminal. Then I see the positive polarity terminal of the 12 volts across my resistor. Then I see V out, set this to 0, and so V out is equal to -12 plus 2, which is -10 volts. Why is it -2? Because we see the negative polarity terminal of the 2 volt source first. We're just doing Kirchhoff's voltage law. So it's like we're writing one of our mesh equations. If we see the negative polarity terminal first, it gets a negative sign. If we see the positive polarity terminal first, it gets a positive sign. Yep. No, I'm talking about this minus sign right here. When we're applying Kirchhoff's voltage law around the loop that I've outlined in green, we're going through the 2 volt source, then across the input terminals of the op amp, then across the resistor, and then across that output. And yes. It absolutely is. That's where the -2 came from. Yeah. Any other questions about this problem? I know it's going to take a little bit for you guys to wrap your head around this because it's kind of a funny looking thing. That's okay. Questions are good. Means you're paying attention. Yes. So if there were a voltage source in series with that current source, is that what you're saying? So let's do another problem that does just that. This isn't on my list of stuff, but let's look at it. All right, so let's say that we have a problem where we have, I'm going to start messing with you guys a little bit as well. Just a little bit. So let's say I have a 3-volt source here connected to a 1 kilo ohm resistor. Separate problem, yes. Let's say that I have a 2 kilo ohm resistor here. Here's that voltage V out that we were trying to find. And then connected to my inverting input terminal, I have, let's call it a 5-volt source here. And a 4 milliamp source here. So the first step that we did in the last problem, and I like it, is that we determined what the voltage was at the non-inverting input terminal. So what should it be here?
3 volts.
Okay, why is it just 3 volts? What does the 1 kilo ohm resistor do?
No, nothing, there's no ground.
Exactly right. That resistor right there, the 1 kilo ohm resistor, cannot have a voltage drop over it because no current can flow into or out of the input terminals. So it does nothing. No voltage drop over it. The voltage present at the non-inverting input terminal is 3 volts, which means the voltage present here at the inverting input terminal is 3 volts. All right. Now, what's the current that I've drawn in red here? 0 amps. Which means all of the current being supplied by my 4 milliamp source flows through my 5-volt source and then comes and flows through my 2 kilo ohm resistor, which will give me a voltage drop of what across my 2 kilo ohm resistor? 8 volts. So what should my output voltage be? Negative 5 volts. Okay. Yeah. So when we do KVL around our path, let's verify it here, right? So let's start here at this ground terminal. Go up across our 3-volt source, across our 1 kilo ohm resistor, across the terminals, the input terminal is the op amp, across our 2 kilo ohm resistor, and then across our open circuit where we're measuring our output voltage. If we wrote our KVL equation, what we would see is negative 3 volts. So this is from that DC voltage source where we see the negative polarity terminal first, plus 0 volts because there's no voltage drop across that 1 kilo ohm resistor. Another 0 volts because there's no potential difference between the inverting input terminal and the non-inverting input terminal. Then we would see the 8-volt drop over our resistor. And then we would see V out. Yes, sir.
In this circuit, what's the point of 5-volt?
Because he asked me what would happen if we put one in.
So it doesn't have to do anything.
No, it's not supplying any power or anything, no. So effectively, what that 5-volt source does, which is going to have, that 5-volt source forces the voltage drop across the current source to have a specific value. But other than that, it does nothing. Is it important that the current source has a voltage drop of a specific value? Not particularly, no.
So the current still stays the same after as long as the 5-volt source?
Yeah, how could it not? They're in series, so they have to be carrying the same current. Yeah, so it's just that 5-volt source is there because he asked me to make the question harder, full stop. All right. If, like, we could potentially write a different Kirchhoff's voltage law loop because we're just starting at ground and ending at ground. We could figure out what the voltage drop over the current source is and all that kind of stuff, but it doesn't help anything. I'm going to continue to just choose that one loop because that's easiest. It's always going to be easiest for us to determine what the voltage drop is at the non-inverting input terminal. It's going to be way easier to figure that out and then use that to tell us what the voltage is at the inverting input terminal than the other way around. Okay. All right, let's work another problem. Okay. The 0 volts represents the voltage drop over the 1 kilo ohm resistor. Right? And there is a 0 volt drop over the 1 kilo ohm resistor because there is no current flowing through the 1 kilo ohm resistor. So it too, for the intents and purposes of this class, is there to make the problem look harder. All right. We're going to talk about using nodal analysis for these guys in a little bit. I would never use mesh analysis with an op-amp. All right, so let's say that we have this circuit. Here we have our op-amp and in my feedback loop, I'm going to have a voltage source in series with a resistor. So let's call this 4 volts and let's call this 6 kilo ohms. Instead of having an open circuit that we're measuring the voltage drop across, let's have a 10 kilo ohm resistor. And so V out just represents the voltage drop over that 10 kilo ohm resistor. And let's say that I have a 8-volt source here. Any thoughts as to how we might analyze this guy? Okay, finding the voltage drop over the 6 kilo ohm resistor. I agree that that is critically important here. What is it, Kyle? Justin, what do you think it is? No. John? 8 volts over the 6 kilo ohm resistor? I disagree.
There's no current flowing into the.
Ian's got it nailed. No current can flow through the 6 kilo ohm resistor because that would force current to flow into or out of the input terminals. So the voltage drop over the 6 kilo ohm resistor in this case must be 0. Right? So I'm going to draw the arrow in the opposite direction here and say that this current represents 0 amps. So what was your question? No. Okay, so let me explain that. That's a fantastic question. Trying to remember what your name is. I want to say it's Brandon, but I also believe that's wildly wrong. Yeah, I'm sorry. I know that that's Brandon, and there used to be a Brandon that sat over there, and I made a terrible guess. What's your name? Please remind me. Kobe Simpson. I apologize for forgetting your name. So Kobe asked, effectively, would the voltage drop over the 10 kilo ohm resistor be 0? And the answer is no, okay? So ideal op amp rule number 1 states that no current can flow into or out of the input terminals. It does not say anything about current flowing into or out of the output terminal. And since the 10 kilo ohm resistor is connected to the output terminal, we might have current leaving out of it. What that current is, I couldn't tell you without figuring out what V out is. So how would we go about figuring out V out in this case? KVL. So if I start here, I go across my 8-volt source, across my 4-volt source, across my 6 kilo ohm resistor, and across my 10 kilo ohm resistor, what I wind up seeing is negative 8 volts, minus 4 volts, plus 0 volts, plus V out is equal to 0, which means V out is equal to 12 volts. Does the size of that 10 kilo ohm resistor matter? As long as it isn't a 0 ohm resistor or a short circuit, the answer is no. It can be anything from slightly larger than a short circuit all the way to an open circuit, and V out will not change. In the real world, we would have to take into account what's called the op amp's output resistance, which is usually on the order of a few ohms. So we would typically want to have a load resistor be on a kilo ohm scale so that it behaves like an ideal op amp. Yes.
How come the 10 kilo ohm matters, but the 6 kilo ohm doesn't?
The 10 kilo ohm doesn't matter. Where did the 10 kilo ohm resistor show up on our equation?
I thought you said it matters if it's a short circuit.
Well, if it was a short circuit, that means that the output voltage would be ground. It'd be forced to be ground. Right? If I make that 10 kilo ohm resistor a short circuit, V out by definition will be ground because it's connected directly to ground. That's the only case where it matters. So if it's literally anything other than a short circuit, that resistor value doesn't matter at all. An open circuit and a short circuit aren't the same thing. So I'm confused by your question. If it were an open circuit, V out would still be 12 volts.
You said if it was a short circuit, then V out would be ground, but V out's not.
No, it's not. I'm saying if that 10 kilo ohm resistor were a short circuit means we connect those 2 points with a wire. V out would be forced to be 0 volts because it is directly connected to our ground terminal. If V out were an open circuit, meaning that there is no physical connection between the ground node and the output node, V out will be exactly 12 volts, which is what we've calculated. All right, let's work another. So notice that I've changed things up on you here, okay? The inverting input terminal is on bottom now. The non-inverting input terminal is on top, okay? I'm a crafty and sneaky person, all right? I'm going to push pause on answering that question for about 10 minutes. Oh, wait, I'm getting my questions confused. I apologize. All right. I would like us to determine the output voltage of this circuit. This is one of my favorite circuits to discuss with you guys. Anybody got any thought about what VI should be? John? 0. Absolutely right. How did you get there? Right. Exactly right. So if we follow this path, where we start here, jump across our terminals, and go like this to ground, what we have is a 0-volt drop over the short circuit that's connected to the non-inverting input terminal, and then a 0-volt drop to get to our inverting input terminal, and then a 0-volt drop over our 3 kilo ohm resistor. So we have V out plus 0 is equal to 0, which means V out 0. Absolutely right. Kobe, where does that 5 milliamps of current go? It's leaving ground. It's flowing into the output terminal, right? So that current has to go somewhere. So it's flowing into the output terminal, which is perfectly okay, right? As long as it doesn't flow into the input terminal, our conditions are satisfied.
Kind of gets dissipated into the op amp.
Well, it's going to wind up going through the power supply terminals to ground that way. Yeah. So it's flowing internal to the op amp until it reaches ground. Absolutely correct. Yes. Exactly right. That's a fantastic way to think about it. It is outputting a negative signal, which means that current is, so if it's outputting negative current, that means current's flowing in. Yeah. Pardon? Yeah, so the current flowing, if we labeled this current as I out, the current flowing into the output terminal, then that would be exactly 5 milliamps in this case. Yes. All right. I have a 5th problem, but I'm going to skip it. So these first four problems that we have worked here are literally the first 4 problems of your web work, but with the numbers changed. What was your question?
For clarification for that last one, the current rule only applies to the negative terminal.
It occurs both to the positive or non-inverting input terminal and the inverting or negative terminal. So no current can flow into or out of either of the input terminals.
But then
It's going into an output terminal, not an input terminal. So that's why it's okay. So the current flowing here has to be 0. The current flowing here has to be 0, but on the output side, it can be whatever it needs to be for these ideal op amps anyway. Yeah. So what we're saying is that this 5 milliamps of current flows up, hits this node. None of it can flow down because that would involve current flowing into the into the inverting input terminal. So instead, all of it has to flow into the output terminal. So that's where the current went. In a practical case like this, which there wouldn't be a reason to do it, it wouldn't necessarily convert to voltage. You would just be driving current through the op amp and syncing it to ground through the power supply connections. So this would be a fantastic way to turn an op amp into a heater until you burned it up from a practical standpoint. But, so from analysis, it's interesting. Doing it intentionally is not the smartest idea. All right, so these are the first 4 homework problems from homework set number 16, but the numbers have changed. There are 2 more problems that I'm going to leave you guys to do of your own volition, although one of them is almost exactly like the in-class assignment problem. Yeah, so what I'd like to talk to be honest, this homework set shouldn't have taken you more than 20 minutes. So now let's look at some op-amp problems that are more like the ones that I would put on the exam. In my opinion, these are all too easy. And so I want to walk you guys through a very simple and straightforward methodology for solving what I would say the overwhelming majority of op-amp circuits are, okay? It actually will work for every op-amp circuit that we'll deal with in this class unless we put a voltage source in that feedback loop. All right, so I'm going to start with a circuit. So let's call this 4 volts, 2 kilo ohms, 6 kilo ohms, and this is VF, okay? Here's what our methodology is going to be. Step 1, and it's not valid in this circuit, but I'm going to mention it because it will trip you up later. Combine any resistors that we can, okay? Like I said, this does not appear in this particular circuit, although I could make it by just, well, actually, let's make it, let's force it, just for the sake of it. Let's put a 1 kilo ohm resistor right here, okay? And let's do another one because I know that this is going to trip you guys up. So I think I put this as a 4 volt. Let's put another 1 kilo ohm resistor right here. Okay. So here's step 1. Make any resistor combinations that we can. So, Cheston, what resistor combinations can we make? Tell me what your thoughts are. Okay, so the 6 kilo ohm resistor and the 1 kilo ohm resistor are in series, so we can combine them together. So let's call this guy then a 7 kilo ohm resistor. Christy, are there any other resistor combinations that we can make? 1 kilo ohm and the 2 kilo ohm resistor are in series. Right? They have the same, will they have to have the same current flowing through them? Yes, they're in series. So I could replace the 2 kilo ohm resistor, or combine the 1 kilo ohm resistor and the the 1 kilo ohm resistor and the 2 kilo ohm resistor to be a 3 kilo ohm resistor. Do they carry the same current? Like literally the exact same current. So here's our 2 kilo ohm resistor. Here's our 1 kilo ohm resistor. I'm going to draw this current. I don't know what it is. There's going to be current that flows from the 1 kilo ohm resistor through the 4-volt source, right? None of that current can branch off. So the 1 kilo ohm resistor is in series with the 4-volt source. Am I correct? All of that current then must flow into the 2 kilo ohm resistor. So if the 1 kilo ohm resistor is in series with the 4-volt source and the 4-volt source is in series with the 2 kilo ohm resistor, then the 1 kilo ohm resistor is in series with the 2 kilo ohm resistor. They all carry the exact same current. So I could change the order of any of those 3 elements and it would not change the behavior of this circuit at all. Benjamin.
Following the logic of the current flowing through that path, does that mean that the 2 resistors we just combined are in series with the 7 kilo ohm resistor?
Okay. So I understand your logic there. And it's not a dumb question, but it's a scary question, okay? And so that's going to screw around with the simple analysis method that I have here. So let's not do that. I understand exactly what you mean. So his suggestion was, since we know that none of the current can branch off and flow into the inverting input terminal, why don't we just lump that 7 kilo ohm resistor there? And the shorter answer is because I don't want to, because it's going to make math funky and I don't want to do that. Yeah. So let's go back to this guy. We're combining the 2 and the 1 to make a 3. Okay. So this is where I want to stop with my resistor combinations. Okay. I have a resistor connected across my feedback circuit, the feedback portion, just one resistor. And I have one resistor between the inverting input terminal and my input voltage source. So that's about as simple as I can make this, all right? Step number 2 will be apply rule number 1. That's the one with the currents, right? I think that's what I said. Apply rule number 1 and determine V plus, which is the voltage present at the non-inverting input terminal. Catherine, could you tell me what that voltage is? Can you tell me what the voltage at the non-inverting input terminal is? Correct. That 5 kilo ohm resistor there cannot have current flowing through it, right? So that's why I said apply rule number 1. So this current has to be 0 amps. This current also must be 0 amps, but we can see very easily then that if the current flowing through the 5 kilo ohm resistor is 0 amps, there is no voltage drop across the 5 kilo ohm resistor, and therefore our voltage V plus must be exactly 0 volts. I'm sorry, Joel, what was that? I applied a voltage source there, I put a resistive divider circuit there, something like that, but for this guy, if it were an open circuit, we couldn't say what it was, but that wouldn't make any sense. We need to have something connected to both the inverting terminal, or inverting input and non-inverting input terminal.
But even if you did have a
Exactly right. All right, step number 3. is going to be apply rule number 2. I can't spell rule apparently. And perform KCL at the inverting input node. So this is slightly different than what we did previously, where we did KVL every time. KCL is going to make our life a little bit easier. And I'll explain what I mean by that in just a moment, right? So if we apply Kirchhoff's current law at the inverting input node, we're going to add this current that I've drawn in blue flowing to the left through the 3 kilo ohm resistor to this current flowing up through the 7 kilo ohm resistor and set them equal to 0, right? But we were applying rule number 2. So what that means is that our equation should look something like this. I'll do it in blue actually. Our voltage at our non-inverting input node was 0 volts, which means the voltage here is exactly equal to 0 volts. So we're going to have 0 volts minus 4 volts over 3 kilo ohms plus 0 volts minus V out over 7 kilo ohms is equal to 0. So if we follow steps in this order, we are guaranteed to have a one equation, one unknown relationship that will allow us to solve for V out in our next step. So in this case, we're going to wind up having V out is 4 volts times a factor of -7/3. And I'll explain how I can do that so quickly in just a minute. What? All right. If you don't believe me, throw this little one equation, one unknown system into your calculator, numerical solver, whatever. Solve it. The answer should be -28/3. Okay. By all means, if you don't believe me, test it. In just a moment, we'll circle back around to where I got the relationship that I used from. Okay. So the next problem that I want to work is going to be similar to this guy, but it's going to be bigger and uglier because it is very similar to what I like to put on your exams. Okay. We are just going to follow those 4 simple steps. So something like what I will wind up putting on exam 3 regarding op amps would be this guy. So it looks like I have increased the level of difficulty of these circuits astronomically. Right? We haven't seen anything that looks anything like this. We got resistors and sources all over the damn place. But we can still apply those 4 simple rules and get a numerical answer for this problem, determining what V out is in a relatively short analysis process, okay? So let's start with step 1. Are there any resistor combinations that we can make? Are there? No. No resistor combination. Step 1, fruitless. What's step 2? Apply rule number 1. So I make a habit of explicitly stating this current is 0 and this current is 0. And then determine what the voltage is at the non-inverting input terminal. Nolan, do you have any thoughts on how we might do that? I disagree.
The 2 milliamp has to go through. It's gonna have a voltage drop of 4 volts.
That's exactly right. So what Ian said, this 2 milliamps of current here will flow through the 1 kilo ohm resistor, and then all of it will flow down through the 2 kilo ohm resistor, which means the voltage present at the non-inverting input terminal with respect to ground, all of these voltages that we're dealing with are nodal voltages, so they're all measured with respect to ground, will be exactly 2 milliamps times 2 kilo ohms, or 4 volts. So this little configuration here tied to the non-inverting input terminal is what we in the electronics business would call a biasing network. So we're establishing a voltage with a particular circuit to make that voltage be there. Obviously, it would be easier if we just put a 4-volt source on there, but I'm trying to test you guys. So I've got to be sneaky and do weird stuff like this. Okay. The only other option would be a voltage divider network or something like that. Talk about a circuit that involves one of those in a little bit. Yes. So the voltage drop across the 1 kilo ohm resistor, no. The voltage drop across the 1 kilo ohm resistor and the voltage drop across the current source add up together to be 4 volts, right? So it's going to be 4 volts no matter how we slice it. All right. So we have successfully done step 2 here. What's step 3? Follow rule number 2. Rule number 2 says that the voltage drop at the inverting input terminal is the same as the voltage drop at the non-inverting input terminal, which means the voltage drop at the inverting input terminal must be exactly 4 volts. Then what do? Pardon? What do you mean by backtrack a source? You're doing all kinds of weird stuff. What does rule number 2 literally say? Apply rule, or excuse me, step 3, apply rule number 2 and perform KCL at the inverting input node. We have applied rule number 2. Now let's perform KCL. Okay. So that's going to be this current. So the 6 milliamp source is going to show up in there. This current and this current all add together to equal 0. So Elijah, do my KCL equation for me. Tell me what should be there. So you've made an assumption there that V out is 0 volts. If we knew that V out was 0 volts, why would we do this analysis at all, right? So it's got to be 4 minus V out. All righty, step 5 would be to solve this guy. Now this one is weird enough that it's not going to have some simple relationship that I can pull off the top of my head, so we'll actually have to use a numerical solver. So somebody do it. Writing on my calculator. All right. Doesn't matter how complex I make this guy, as long as it doesn't contain a voltage source in the feedback loop, this method works. Yes, sir.
If it were, could we just fairly trivially do a super node and just have both relationships between them?
Sure. I think that should work. Yeah.
It wouldn't really have that much complication.
No.
Make the KCL slightly.
Right. I have never experienced any practical reason why you would actually put a voltage source in the feedback loop. I didn't write those first few problems or whatever that have them in there. I think it's just to kind of be tricky and all that kind of stuff and enforce using the rules more so.
I think you forgot to tell 6 not 6
We'll vote for 4 kiloohms is 1 milliamp.
that's
We multiply that by 5 kiloohms. Negative. Got 4.
Okay.
Yes.
Okay. All right. Any questions on this stuff? Anything else? All right. We got 30 minutes left of class. Let's do the in-class assignments.